what is regarded as weightlessness? Write it down. Weightlessness. Is a condition where there is only one force acting on you, and that is your own weight. Weightlessness is a condition where there is only one force acting on an object, and that is the object's weight. Weightlessness is a condition where there's only one force acting on an object, which is the object's weight. So, am I experiencing weightlessness right now?
No.
Why?
No.
Because there's a contact force acting on me, reminding me that I'm heavy, and all that, right? So the contact force is what tells you or reminds you of your weight. Now, the contact force is not there, and then you can actually experience the same weightlessness, that people in space or in a satellite can experience. All right? So weightlessness is a condition where there's only one force acting. Can you say that when people experience weightlessness, there's no weight acting on the person? No, weight is acting everywhere. Wherever they go, there is always a weight. It may be smaller, but it is definitely not zero. So weight is something that's always there, but weightlessness is when only one force is acting on an object, which is your weight. To experience it, maybe you can go to the top of a building and jump off from there. So when you jump off, what is the force acting on you? Don't do that. Gravity. Gravity is the only force acting on you, and so you can experience weightlessness there. You can roll whichever way you want. The same feeling but as time progresses, as you start falling faster, then what happens? Air resistance comes in, and therefore you will not really enjoy that weightlessness condition. Weightlessness is when nothing else is acting on you. You are actually in free fall. Then it is weightlessness. Okay? You experience some of it actually when you go over a hill with the car. As soon as you kind of go over a hill, the car is basically falling and you are falling with it. And so do you feel that? Kind of a gasp. That's weightlessness, because that's the moment when you are actually falling with the car and the contact with the seat is not much. And that is why you experience that condition for a little while. Okay, only for a little while. So you experience that even in roller coasters. Okay, we'll go into those things later. Let's look at other problem situations. Objects in equilibrium. What happens when forces act on an object in such a way that the object is in equilibrium? What does the word equilibrium mean? The net force is zero. That's what equilibrium means. Equilibrium means the net force is zero. So when you say something is in equilibrium, the net force is zero. So what should be happening to the object when the net force is zero?
It should be in the same state of motion.
It should be in the same state of motion, meaning?
It is not accelerating.
It is also meaning?
Constant velocity.
Also meaning it can be at rest or moving at a constant velocity. When you say constant velocity, zero is also a constant velocity, right? So everything that you said is right. So what it breaks down to is when an object is in equilibrium, the object may not move or move with a constant velocity. Which law of Newton reminds you about that? The first law. So equilibrium basically is about the first law. So let's take a problem first of all and then decide about. Now if there is a wall on this side and there's a wall on this side and there is a cable stretched between the two, like between that wall and between that wall, a cable is stretched between the two, or a rope is stretched between the two. And right in the middle, you attach one more rope. Okay? Right in the middle, if you attach one more rope, and if you hang on that rope, then what will happen? The rope is now like this. The rope is going to stay like this. So this is you hanging on it. So now the rope is not there, it's come down here, sagging. Can you see the actual rope position is this? This is not the real rope. And now if you are 100 kilograms, now when I say hanging, not by the neck, by your hands. Okay. All right. So, just clarification, just so you're just like hanging onto there, either by using a rope or anything, and that's you. And if this angle, when you do so, is 20 degrees, there are two sets of forces you can see. There's one object is acted on by a couple of forces. What are the forces acting on this object? That is you. What are the forces? Yep, gravitational force acting downward. How much? 980 newtons. The gravitational force acting on it is 980 newtons. On you is 980 newtons. Is there anything acting on this one here? The tension. And do you have an idea of how much the tension is? It should be 980 because it's in equilibrium. Exactly. That should be 980 also because we're already applying the first law. The net force acting on you should be 0 because you're not moving. You're just hanging on it. So the net force on you is 0, which means the downward force and the upward force should be equal and opposite. So tension is 980. So we solve that by considering the equilibrium here. Now let's look at this knot. Is a knot acted on by forces? Which forces? Where? The knot is not an object, but it is definitely a junction point. Yes?
Tension?
Tension acting which way?
Downward.
Downward, how much is it?
980.
980? Because from this point to this point is one rope. And the tension in one rope has to be the same. Right? So from here to here, the tension is 980. Then what else? What else is acting on it? On this knot? Yeah.
The tension from the knot going to one side.
The tension from here,
Yeah,
doing what to the knot? Pulling it that way. Yep. And then this way. This is the same tension.
yeah, because the,
How do you know?
because it's a single
Yeah.
knot.
Yeah, but those are justifications. Do you, have you proved it? You're not proved it, you're just guessing it. No guessworks in physics. Alright, if you do not know, just take it differently. If you do not know anything, just take it. By the symmetry of things, you may say, oh, it should be the same. It should be, yeah. But unless you prove something, you are not supposed to take it for granted. So, yeah, we don't know about tension T1 and tension T2, like take it as it is. Now, this knot is acted on by three forces. There's a tension pulling it that way, there's a tension pulling it this way, and there's a 980 newtons pulling it downward. And do you think this knot is in equilibrium, or the knot is not in equilibrium? It is in equilibrium. That means the same condition can apply once again. The net force acting on this knot should be 0. Now, when you say the net force is 0, as you can see, the forces here are all in different directions. We can actually break this down further. Summation of all the x components of the forces must be 0, and all the y components must also be equal to 0. Is that right? If the resultant is 0, can you say the x component and y component don't exist? Is it possible that resultant is 0, but there is some x component but no y component? Is it possible that way? Can you have an x component or y component and still have no resultant? That's not possible. Because the resultant is square root of x squared plus y squared. So if x or y exists, then the resultant cannot be 0, right? Impossible. So if the resultant is 0, we can easily write this condition also. Summation of all the x forces must be equal to 0. Summation of all the y forces must be equal to 0. Sure conditions. What do you do now? We're going to resolve it, because that's how we can tackle these forces. So we resolve it. And how do you resolve it? You take this as your y-axis and consider this to be your x-axis. And we're going to make the table, remember that? We can make the table horizontal or x or vertical or y. Components. Now let's list the components one by one, right there. What is the horizontal component of tension T1? Can you see this? If I break T1, T1 has got one component here and the other component there. So what is this component? Now that is 20 degrees. What is this angle? 20. So what is this component? T1? So T1 cosine 20. And what is the y component of the same thing? T1 sine 20. Griffin, tell me the next one. What is the x component of this? T2 has got two components. One is this and the other is this.
T2 cosine 20.
Is it right? T2 cosine 20? Are you 100% sure?
Not really.
Everyone?
Yes.
Huh?
Is it negative?
It is negative. Don't forget it. It's going the other way. Don't, every time you come up to some components, you should think about it. Is it positive or negative? Just think about it. Automatically, you'll be, you will sometimes be reminded, oh, it is negative. So don't forget. Every time when you write a component, discuss whether it is positive or negative. So this is negative T2. What about the y component? Positive T2 sine 20. Now let's take the other force, that is 980. What's the x component of 980? 0. And y component? 980? Negative 980. Because it's downward. So we have done resolving. Now we got to add them up. We got to add them up. And when you add them up, all these forces in the x direction must be 0. And all these must be equal to 0. So we are adding them up here. So T1 cosine 20 minus T2 cosine 20 plus 0 equal to 0. What does it tell you? T1 cosine 20 is equal to T2. And now what do you say? Now we have proved that T1 and T2 should be the same. We have proved it. So no more guessing on that. On the other side, same thing. Add them up, equated to 0. So T1 sine 20 plus T2 sine 20 minus 980 equal to 0. Write down, Griffin, write down. Now since T1 and T2 are the same, I'm going to replace T2 with T1. Right? So it will be T1 sine 20 plus T1 sine 20 equal to 980. So it will be like 2 T1 sine 20 is equal to 980. Do you understand that step? I have replaced T2 with T1 and I see identical pairs of things. So it's twice equal to 980. So how much is T1? Calculate. Tell me how much it is. How much is T1? The tension in the upper cable. Yes, 1432. So tension T1 is 1433 newtons. If you got something in 500s, check your mode on the calculator, be maybe in radians. And I think in your case, you must have
Yeah, I put in
parenthesis under that. So if you don't put parentheses, then you'll get totally different. All right, so tension T1 is 1433 newtons. Make sure you do the calculations right. Yeah, plug it in, see how it works. So tension in this cable is 1433 newtons. And obviously this one is also 1433 newtons because we proved that they're both the same. What are you trying to carry? 980 newtons? And these two strings are developing a tension of what? 1433. So you can actually bring a force in a cable more than what you yourself can weigh. You get it? What if that angle is smaller? What if the angle is 2 degrees? Like you tied it tight and then you hung from the middle and the rope did not bend, sag much, it just like 2 degree angle. How much is it then? If you put 2 degrees here, what will be the tension? Recalculate it with 2 degrees. Make sure you don't make a mistake now. Yes. 14,000. Yeah. 14,000 newtons when your whole weight is only 980 newtons. 14,000 newtons you can actually create in a cable. In this thing. Now where can you apply this?
Zip lines.
Huh?
Zip lines.
Zip lines? Yeah, zip lines. In fact, you're right. Zip lines, you may weigh just a normal amount, but the tension in the cables will be enormous. That's why the zip lines have to be really strong enough to withstand all those tensions. Yep, very important, that one. Yes. Bow and arrow. Exactly. As you pull. But there is already a sag, and that really helps. If there is no sag at all, that can be difficult. Typical example I show you. Imagine your car is stuck in the mud or something like that, and it's not coming out on its own. So you need to pull it out from outside. So if I tie a rope onto it, and if I come to the front of the car, and if I pull it, can you pull it out? If the car is not able to come on its own because the wheels are spinning, Griffin is tying a rope and coming to the front of the car, and he's trying to pull the car. Will it come out? No, it's not easy. But can a person individually do it? Yes, it is doable. How can you do that? All you do is take a rope or a cable, and find out if there is any tree or any strong support anywhere. Okay? And take this rope and tie it on that tree. Take the rope and tie it on the tree. Take the rope. You understand what I'm saying here? Take this rope and tie it on a tree somewhere. And then what do you do then? Go to the middle of this rope and just pull it that way. Now when you pull it that way, what happens to the tensions here? It'll be far more than what you can actually produce by your own weight. So you can actually apply a pulling force on the car which is far more than what you can actually really apply. This is application. You understand? The same thing, like for example, if a metal wire, you want to snap a metal wire and you are not able to break it, you want to just break it for fun. So if you just take the metal wire and just pull it like that, when you take the metal wire and just pull it, will it break? It is not going to break that easily. When you take a metal wire and use your hand strength, it's not definitely going to break. But is it breakable by you alone without anybody else's support? Yes. What you do is take the wire and tie it between two strong supports. between two strong supports. Tie it. Okay, tie it onto this knob. Tie it onto that knob. Tie it tight. And after tie it tight, go to the middle and just pull. Go to the middle and then just pull, and you'll see that metal wire snapping off easily.
Extra.
Oh, yes, really.
Like, what it's snapping.
It may snap from somewhere, not from the place where you applied.
But it's gonna snap.
Yes.
Yeah, it, like normally when you cannot break like that, it's easy to break that way. So if you have a clothesline or something like that, you just pull it from the middle, it will snap easily compared to you pull this way. All right. So sometimes we need to apply common sense when you apply forces, because you should kind of estimate as to where the forces are going to be bigger and so on. Let's say, for example, you have a box that weighs 100 kilograms. You have a box that weighs 100 kilograms. And you want to transport it from here to student affairs. And yeah, one option is you carry it yourself and then take it. How much force should you apply to take it like that? 980, right? You pull it with 980 and you can just go. That is one option. But then you discovered you have a friend to help you. So what you're now doing is you call your friend. But of course, you know, since the boxes, it's not easy for both together to apply the force. Now what you're doing is you are carrying it by using a rope, because you didn't find anything. So you're passing a rope through it, and then you're going to carry. So you're carrying from here, your friend is going to carry from there, and the force downward is 980 newtons. And if you're going to carry it like this from here to the student affairs, that's a foolish thing to do, because how much force are you supposed to apply here? If the angle is 20, 1433 newtons, when you need to only apply 980 to carry it yourself. And with the help of your friend, you're applying 1433, your friend is applying 1433. You understand this? So that will be it's a wrong design. That's not the right thing to do, to carry it, because you end up applying more force than you alone, what you can accomplish yourself. You get it? Another option is to look for a pole. Look for a pole, pass it through there, and then you pull from here, and your friend pulls from there, and then you just walk like that. How much force should you apply here now? 490 each, which is good, right? So now it's 490 and 490. And in the previous case, you were pulling against each other for no reason. There was a horizontal component applied by you, and he was also applying a horizontal component, fighting with each other basically, and that was doing nothing. The carrying force was very small. Okay, so in this case, 490, you have to apply only 490 and you can get the job done. All right, so you saw how objects got to be treated when they are in equilibrium. We will get back to equilibrium and Newton's laws a little later. Before that, we need to cover up something more, which is friction. Okay? So once we cover up friction, then we will go back into the similar problems and then use friction along with it. Now, in most of the problems we said, oh, forget about friction, forget about friction. So things were very easy. But when friction comes in, you'll see how it changes the whole situation. So what is friction? Friction is a force that opposes motion. Friction is a force that opposes motion. And we saw that in molecular terms, in atomic terms, in microscopic terms, we saw how friction actually comes in, because the surfaces are not absolutely smooth. the surfaces cling with each other, right? The atomic strands, they kind of link with each other, and that is what causes the grip. So friction, what does it do? It kind of opposes the motion. Now there are two kinds of friction. Fluid friction and then solid friction. What is fluid friction? It's a friction between two fluid layers. What's a fluid? What's a fluid?
A liquid.
Is it a liquid?
Yes.
No?
More of a distinction.
A fluid is anything that flows. Any substance or any material that flows is a fluid. Now, can you say what's a fluid? Yeah, so examples, like what kind of substances? That's a liquid also, right?
Same.
Gases and liquids are considered fluids. Can gases flow? So they are fluids. Air is a fluid. So we are right now at the bottom of an ocean of air. Imagine it that way. So this is fluid. The only thing is it's less dense. It's not like water. Water is more dense, but this is less dense. But we are, that's why I said the atmosphere is approximately 50 to 100 miles thick. Now, we are at the very bottom of that ocean of air. So we are creatures at the bottom of the ocean, but the ocean is air. But unlike water, this ocean is different. As you go higher and higher, it becomes less dense. So when you go to 50 miles height, there are a couple of atoms here and there, that's it. But the densest air is on the ground level. So here we have the highest amount of air. Now if you go to higher altitudes, the air quantity is less, which means the oxygen is also less. So which means if you're going to take, practice running at a high altitude, at high altitudes you don't have much oxygen to breathe, and so running can be difficult, challenging. So that's why some of the runners, they go to higher altitudes and practice over there, and then when they come run ground level, oxygen is not a big issue, right? Anyway, so fluid is anything that flows. Now, what do you mean by fluid layers? Fluid layers, okay, air is a fluid. There are different layers which you cannot see. You're not able to see those fluids, layers, but we can always imagine its existence. Now, normally we are not talking about fluid friction by considering two fluid layers. No, I mean, yes, two fluid layers, but we are always referring to an object. Now, what is the object? Maybe me. If I am in the object, is there a layer of fluid stuck to my body?
Yeah.
Bonded to my body? There's a layer of fluid, right? Outside my body, is there a layer of fluid? Yes, which is not connected to my body, but that's the next layer. So when I start moving, what am I doing? I'm trying to carry the layer which is stuck to my body with me. What about the other layer? It's left behind, right? So when that happens, the two fluid layers are going to rub against each other, causing a little drag. And that is called fluid friction. So let's take your car. Your car, the body of the car has a layer of air surrounding it, which is belonging to the car now. So wherever the car goes, that layer goes with you. But there are layers of air outside the car. So when your car starts moving, those layers will start rubbing against each other, causing the so-called drag. Okay? And that's called fluid friction. You get it? Yes. Another example. Let's take a jar of water. You drop a steel ball into the jar of water, and you'll see the steel ball going down. Now, these are all imaginations that you should be able to, I can't demonstrate all these things for these silly things, but, you are capable of getting that imagination working right here. So imagine there are two jars. One is a jar of water. I drop a steel ball, and can you visualize the steel ball going down? There's another jar of honey. Take the same steel ball and drop it into honey. Can you visualize how it will go? Slower. It's going to go slower because there's a lot of drag there, right? There's a lot of drag between the layers. So fluid friction depends on what factors? Depends on viscosity, which is basically the nature of fluid. It's called viscosity, as he said, but we don't want to go that far into it. Yes, it is. It's called viscous forces, viscosity. But what does that viscosity depend on? It depends on the nature of the fluid. Is it honey, or is it water, or is it, gasoline? Okay. Or lubricant. A lubricant, the purpose of that is to avoid friction. So the less friction between those lubricant layers. So it depends on the nature of the fluid. What else does fluid friction depend on? What else, Michael? Fluid friction depends on?
Density.
Density is part of the, viscosity. Let's say, imagine there are two people standing in knee-deep water. Can you imagine that? Knee-deep water. Two people are standing. One has fat legs, and the other one has blade-like legs like this. So one has got blade-like legs, and the other one has got fat legs, and they're both trying to walk in the water. Who will experience more frictional force? The fat one. So what's the factor here?
Surface area.
Surface area depends on surface area. Okay, you know how to walk on a treadmill, right? On a manual treadmill, not an electric one. Manual treadmill. What do? You grip and kind of pull the belt backward. So when you are able to successfully pull the belt backwards,
You double in trouble.
all right, so when you pull the belt backward, the belt is rolling backward, and you stay in the same place, right? So that's how you walk on a treadmill. You stay on the same place, and the belt starts moving backward. So you're successfully pushing the belt backward, and you're able to stay there. You're successful there. Now, can you imagine, in circuses you must have seen that. I don't know if you've seen, there'll be a tiger sitting on top of the globe, or a ball, big ball, and the tiger will be walking on the globe. So what will happen to the globe? Rolls back. So the globe is rolling backward, and the tiger always is perched on the top. Have you seen that somewhere? Okay.
Let's see if what happened.
Oh, there is the animal that starts walking inside. You must have seen that one. The hamster.
Oh, yeah.
Okay, so in all these cases, what is actually happening is, okay, if the tiger is sitting on the top, it is pulling the globe backward. And is the globe going backward? Yes, and therefore the tiger is always at the same spot. Now we are also like little tigers on this big globe, so-called the earth. We are on the big globe, such as the earth, and we are attempting the same thing. We are trying to grip the ground and push the earth backward so we can stay on top. And we fail miserably. And that's why we end up going forward. So the earth stays there. So imagine The tiger is walking and suddenly somebody stopped the globe. What will happen is the tiger will go forward, right? And that's exactly what is happening to us right now. We are attempting to roll the earth backward so you can actually get to the next place. But we fail in that attempt of rolling the earth backward, and as a consequence, you start moving forward. That is called walking. Man, in an effort to roll the earth backward, fails miserably, and as a consequence, moves forward. That is walking. Anyway, so what is helping you to walk forward? Friction. What is the main driving force for your car? Friction. Without friction, your car is not going anywhere. You may have full tank gas, best tires, all the best cars with all the best features, but the car will not go anywhere without friction. So what helps your car to go forward? What's the main driving force for a car? Friction. What is the main driving force for a train? Friction. Without friction, nothing is going to go forward. But friction is also bad. We try to get rid of friction at many places, right? Like ball bearings, we try to put ball bearings, lubricants and stuff like that to get rid of friction. But at the same time, friction is very good as well. Without friction, you're not going to I can't just keep the book like that. No, friction helps me. Now, if friction was not there, what will happen if I throw the book? It will go off. It will be a terrible world without friction.
Imagine how that would be. You just gotta keep all this stuff on your desk constantly.
Yeah.
It's falling off again.
I mean, friction actually kind of really, without friction, sometimes you must have noticed that, like you try to keep something and then it just, you just try to keep something and it goes off. I didn't expect it to go all the way, but it actually went on. Why? Because between the paper and the table, there was a layer of air. And so it started floating on it. Fluid friction. Of course, less than solid friction. So friction really helps. We are expecting that to be there so that it'll stop. When you apply brakes in your car, you're expecting that force to exist. Otherwise, so what happens when you have an icy road? That's what people misunderstand. Icy road. They think they're driving the same way as a normal day. And then they just follow the next car. And as soon as the other car applies brakes, they just hit the brakes and there goes. So lack of friction on a certain day is what messes things up. So when you know that the road is wet, when you know the road is icy, or there's snow on the road, you must be maintaining a good distance and knowing that applying brakes may not stop your car. And that sort of thing will help you to kind of control your car. Okay? Yes?
Is one kind of friction more powerful than the other or greater?
What is the kind you're talking about?
Between fluid friction or solid?
Solid friction is of course greater, comparatively. Fluid friction is basically the air resistance is fluid friction. It depends on the relative velocity. So when you're driving your car at 35 miles per hour, you're not fighting too much air resistance. But if you're driving a car at 70, 80 miles per hour, then you're fighting a lot of air resistance. Right? So air resistance is an important thing. That's why the body of the cars are streamlined so that you control that part. Now we are going to focus our attention not on fluid friction, but on solid friction. But understand fluid friction is there. When I drop something from like that, it's going to suffer the fluid friction part of it. Why there is a fluid friction when I drop this? There's a layer of fluid around this marker, and there are layers of air outside it. So when this thing starts moving, the layer of air outside it and the layer that moves with it, they both rub against each other. And that's what causes friction. Solid friction. Depends on factors. We saw already the factors that solid friction depends on. Now, watch this book again. What is the frictional force between the book and the table right now? What's the frictional force between the book and the table right now? Nothing?
Friction is force that opposes motion. There's no motion.
The answer is there is no friction. Yes. No friction. Why? Because there is no attempt to move this book sideways anywhere. The book is there, and the book is absolutely comfortable there. It is not fighting against some forces trying to drag it sideways. And therefore there is no friction. Okay? I'm applying a force now, 1 Newton force. The book is not moving. How much is friction?
One.
Is it 1 Newton, less than 1 Newton, or more than 1 Newton?
Less than
Yeah,
1
one.
Newton.
It's equal to 1 Newton because the book is not moving according to first law. The forces must be equal and opposite. So I applied 1 Newton, friction is 1 Newton. Now I'm applying more force, 2 Newtons. How much is friction now? 2. I apply 3. It's also growing. Friction is coming and coming into existence depending on the need. Right? So I keep on pushing and the friction force is building up. But between me and the book, there is a limit for the book, but there's no limit for me. I can keep going, but the book has its own limit. That is called limiting friction. Limiting friction, maximum friction. So the book, let's say, has got maximum friction of 10 newtons. So I apply 9 newtons, it's not moving. I apply 10 newtons, it's not moving. And apply 10.001, and the book gives off. So the grip was going on till that moment, and that's called the limiting value of friction, the maximum value of friction. So frictional force, the maximum frictional force is proportional to what? To the normal force, normal reaction. It is proportional to the normal reaction, the contact force. If there's a good grip, then it's definitely going to be bigger. The force that you need to drag something is directly proportional to the normal reaction. Okay? So the normal reaction. And of course, there is a constant of proportion. So the frictional force is equal to a constant of proportionality times the normal reaction. And this constant of proportionality is called coefficient of friction. That is called coefficient of friction. And this one is the normal reaction.
What is that? Is that an M?
Which one? Mu.
Okay.
Like micro. We use micro as a prefix. Now this is mu as a symbol used just for coefficient of friction. So if it is coming in an equation in mechanics, it is coefficient of friction. If you see in mechanics, you see mu into an equation, most probably it is coefficient of friction. Yeah,
Is that not exactly like the symbol for micro?
yeah, it is the same symbol.
Because wouldn't that be confusing?
No confusion, because when you're using it as part of a unit, then that is micro. When you use as part of an equation, see that's an equation. When you use part like F is equal to ma, you should not be confused with that m. You never asked me that question. F is equal to ma, but m is also standing for meters, right? M is for meters. So there's no confusion there. As long as it's a part of an equation, you know its mass. If it is part of a unit, then it is milli. Yeah.
Just curious, can you have something like a micronewton or something like that?
You can have micro. Oh, you mean micro? That's why I don't want to write n, but I am writing nr. You know what I'm writing nr? And some books write Fn for normal force. So yeah, so you're not going to get mu n. Because if it's mu n, it can be micronewton, as you said. Perfect. All right, so coefficient of friction. And what is the coefficient of friction? It is the kind of a grip that you can have. Now, watch again. So when I apply 10 newtons, it just starts slipping. And once it starts slipping, it's easy to keep it going. It's easy to keep it going after it slips. But before it slipped, it was tough. Before it slipped, it was tough. But after it slips, it's easier. Why?
Because the friction's gone.
The pressure is still the same, but the grip is not 100%. You know what I'm saying? The grip is 100% when it is at rest. Now see, the grip is going off. And at the moment it starts slipping, you can't get the perfect grip like how it was gripping at rest. You can't get it back. An example is this. Imagine there are lots of steel poles. Okay? There are a lot of steel poles on a fence, let's say. Get it? A fence and a lot of steel poles. And your friend is trying to drag you from there. Your friend is trying to drag you from there. And since your friend is dragging you like this, you just somehow manage to hold one of these poles on the fence. And your friend is pulling. Now, if he's pulling gently, you can still hold on to it. You can hold on to it. Hold on to it. You can actually hold on with all your might when you're holding. The moment your grip kind of goes off, and then what's happening is you're on the move. You're on the move. But are you able to still do some grabbing? Yes, you can still grab, like one after the other. But will it be as strong as when you're holding it on one? Never. And that is why friction, there are two kinds of friction. This coefficient of friction, there are two types. We have mu s and we have mu k. And this is coefficient of static friction. And this one is coefficient of kinetic friction. So you'll see coefficients are different. Mu s, mu k, different coefficients. Different substances have different coefficients of friction. Now, you will be told how much the coefficients are. Okay? Now, static coefficient and kinetic coefficient. For example, rubber on road, the grip is pretty strong. But rubber on wet road is not the same. What about rubber on road? The grip is very strong when it is at rest. But on the move, like if you slam the brakes and if the tires are kind of grinding on the road, then it is less. So mu k is always, so mu s is generally greater than mu k. Mu s is generally greater than mu k. Rubber has a coefficient of static friction roughly 1. It's very strong, I'll show you right now. So the equations for friction, you can see there are two equations. One is the maximum value of static friction is mu s times n r, or the maximum value of kinetic friction is mu k times n r. Now, when you use this equation for friction, when it is moving, and when you use that equation when it's at rest, not moved yet. You get it? Now, how do we apply this equation is what I'm going to show you through a problem. Here we go. We worked on this problem earlier. I'm going to take the same problem. The mass of this one is 10 kilograms. The mass of this is 10 kilograms, and you're pulling it this way. I remember 40, is it? There was a problem like that? At an angle of 30 degrees, is that right? Huh? 20 degrees?
No, 30.
No, it's 30.
30? Yeah.
Everyone's is the habits.
So it's a 10 kilogram object, you're pulling it like that, and I said there was no friction at that time. But now I'm saying there is friction. The coefficient of static friction is 0.3, and the coefficient of kinetic friction is 0.2. So, can you tell me what will be the when you're pulling it from there, it starts moving. It starts moving. What is the acceleration? So you're going to find the acceleration. So how do you work with this? Since I'm saying it's already moving, which friction are you going to take into account? The kinetic one. All right. So how do you start working on this problem? First thing first, take the forces. What is the force downward? 98 newtons. What else?
98 newtons up.
No. No. There is a normal reaction, we don't know. Then split this into two components. How much is the vertical component of that? And how much is the horizontal component of that? The vertical component is 40 sine 30, which is 20 newtons. And this one is 40 cosine 30, which is 34.64.
How'd you know that?
40 cosine 30, plug it in and see.
I just want to know how you.
Oh, how I know? Because I know that cosine 30 is square root of 3 over 2. Square root of 3 is 1.732. 1.732 over 2 times 40 gets you 34.64. Yeah. So this is 34.64 and that is 20 newtons. Now tell me what's the normal force. You know that this object is not going upward or downward, so the net force in the y direction must be
78.
0. So this must be 78, correct.
Hey.
You understand why it is 78? Because what's the downward force here? 98? The total force is upward, should match up with 98. Because already 20 is acting here, so what this needs to apply, the contact force is only 78 newtons. What else is acting on this? Friction, this way. And that is kinetic friction. How much is the kinetic friction here? It's supposed to be mu k times normal reaction. Mu k is 0.2. Oh. You may have an issue.
15.6.
No.
Okay, go ahead. How much?
Yeah, 15.6.
15.6. So there is a frictional force of 15.6 newtons acting backward. Now you're going to apply the condition for horizontal net force equal to 0. Horizontally net force not equal to 0. Mass times acceleration. What is the net force? Which way is it going? That way? So which force is bigger? 34.64 is bigger or 15.6 is bigger?
34.
So 34.64 minus 15.6 is equal to MA. And now you get the A. How much?
Oh, not the acceleration.
1.9 meters per second square. So the acceleration of that object is 1.9 meters per second square. Did you get it? Another problem. So yeah, this is the basic idea. You should be able to discover the frictional force by using that equation F is equal to mu times normal force. Questions here? Oh, good. Now you should be able to complete that homework and then we should be able to do more problems on using friction as we go on.